Okay, so what we can do then is to look at the element forces, the body forces. And what we see here is now that potential energy expression. So to make the potential energy expression relate to what we've done, the weighted residual approach, you can just imagine that these U's transposes are just those weighting functions. Okay, as opposed to the displacements like here, they are just weighting functions. So you can imagine this U becomes a W transpose F, where we can write down the W transpose as essentially the shape functions. Yeah, so W equals to N and the coefficients with W. So think of it like that. We know now that this W will have a W1 to W8 then. Although the book does it now in terms of displacement because of the potential energy expression, we do it in terms of the weighting function. Okay, that's one thing just to take note of. And so when I have that, when I look at this expression, it's U transpose F. So this U transpose is essentially a 8 by 2 matrix, because remember U is just a 2 by 8. Sorry, a 2 by 1. The N is a 2 by 8 and Q is a 2 by 1. So this whole expression becomes a 2 by 1. And so this U transpose will be a 1 by 2. And this F is a 2 by 1 vector with two components, Fx and Fy, and that becomes a scalar. So this is a volume integral over the scalar. But to get a vector expression for our loading, we take the derivative with respect to these coefficients Q. The weighting function ones, W1 to W8, and then this will become essentially a vector, a eight-noded vector. That's essentially what we will see there. Okay, and we can already see a glimpse of that because N we know was 2 by 8, N transpose is 8 by 2. Yeah, so this is the expression that I would have for element body forces after I've taken the derivatives with respect to the weighting function coefficients. This is what I would get out, because this is an 8 by 2 times 8, 2 by 1, and that is a 8 by 1. So this is an 8 by 1 vector that we see there. And so what we have is just the N transpose det J, and then this is pulled out because it's constant in this example, but it doesn't have to be constant. If it's a function of sine eta, you have to keep it inside and do the integral with that, and choose the appropriate Gauss quadrature rule so that things make sense. Okay, so this is just what we see here in terms of body forces. Okay, so that's how we go about computing about body forces. To go and compute tractions, well, first thing is, if we want to go traction, we have to evaluate the shape functions then at the right place. So let me see if is this the only, what type of shape is this? A constant traction, Tx, Ty. Okay, force per unit area, that's applied, they say here on H23. So H23, let's go to 3. Where's H23? That element, edge 23, so this is essentially this edge here. So what we have to do is, we have to go and say, we have to evaluate the shape function at that at psi equals to plus 1. That's important. Okay, so that's essentially, we're going to have to first evaluate the stuff at the right place. So what you can say is we can evaluate that expression for our shape functions. Our shape function is now that 8 by 2. Yeah, so because we also have now expression for our tractions, which was the area integral. So it's unfortunate I didn't give it here, but it was essentially the area integral of N transpose tractions. But we evaluate the shape functions at psi equals to 1. That is important. So you can see here N1, N4, N1 are 0. It's only N2 and N3 that are non-zero. And so this is after so this is then related to N2, and this is related to N3, this is related to like N1, to the X and Y component, and N4, X and Y component. And so this is then expression for the tractions that you will go and compute. Okay, after you've done all your integrals and stuff like that. So this is just to make sure that you understand that. The difference here with the tractions are just that we have to evaluate at the right place. Okay, so we'll still look in more detail than that at a later stage. So this is now for the loadings for the Q4 element, numerical integration. So we've gone through this. You can follow through this, read through, feel free, and see the two-dimensional integrals. Quite simple. That's that. Then stiffness integration. We have this stiffness. We have to figure out what is the highest order polynomial here, and make sure we choose appropriate Gauss quadrature rules, and then we can do the integrals of this. Okay, so we sort out the locations of that two-point Gauss rule. So it becomes sort of a 2 by 2. It's 4. 3 rule becomes 3 by 3. It's 9. 5 point rule would be 5 by 5, 25 points that you'd evaluate that by. Okay, so that just make sure that we comfortable with that. And just again, summation. Sorry, after we've evaluated at the right places, and then stress calculations afterwards, we can just write as dBq over the elements. So stress is a function of sine eta in an element, or it's a function of x and y. We first have to figure out which element is the right element for that x and y coordinate, and then relate the x and y back to the sine eta to evaluate those expressions for stress. Okay, so that's really what we have there. Higher order elements follow exactly the same argument. So what we have seen here is essentially here, maybe something I should have highlighted in the quadrilateral element. If you can look at the shape function, you can convince yourself to see that there are linear terms in sine eta, but there's also a coupled term. And the same for the higher order Q8 element. Like we've seen when we did the derivation, there's also these higher order coupled terms. That's x eta squared, or it's eta psi squared eta. So that's that. Okay, so when we look at this, this is now for a 9-noded element, node in the middle. It's called the bubble element. So this is essentially the 8 nodes on the side with the mid-side nodes, and then one in the middle. It's quite Q9 bubble element. But the one that is highly recommended to always use when you're not sure what to do is use the Q8 element, the 8-node quadrilateral. It's called the Q8. And we've already looked at the derivation of the shape function, so we understand where this comes from. You can go and convince yourself that each one of these shape functions to satisfy what's supposed to satisfy, that should be 0. And then the last thing that I want you to do is go and add them all up and see that it's equal to 1. Okay, for all of these elements, add them, always add the shape functions from n1 to 9, n1 to 4 for the Q4 element, n1 to 8 for the Q8 element. Go and add those shape functions up and see for yourself that they always add up to 1. Otherwise, we don't have that rigid body motion condition that is satisfied. Okay. There's a discussion here about integration on triangles. I would avoid that because this is just a very different way to do an integral. It's called the area integrals. I'm not going to waste time on that. I don't want to. This is just understand that all of these things are just ways to do the integral. It's also based on so often these area integrals can be done analytically. These integrals can be done with sort of area integral expressions. Okay. There is one thing that's important to talk about, and that is the idea of the degenerate elements. So, for one, when we have mid-side nodes that are not in the middle, it's part of mesh distortion. That's one way you can distort a quadrilateral element. So let's go back to this quadrilateral element and talk about mesh distortion first. So whenever I have an element, let's just go back to a picture of the element. Whenever I have, where's the picture of the element? When I have an element, and whenever this element is not a square or a sort of a parallelogram type of thing, or it's not that kind of shape, then it's a distorted element. And what it means is just that the Jacobian is not going to be a constant. So as long as the Jacobian is a constant, then things are it's called undistorted element. But as soon as the Jacobian becomes a polynomial, we're going to end up with the same examples we did in the 1D case, having polynomials divided by polynomials. We're making integration error. So the one way to distort an element is this way, where we essentially don't have something that is nice and rectangular, or something that is sort of a nice trapezium, or what do we call it, parallelogram kind of thing, where the height stays constant and where the horizontal stuff also stays constant, just translates a little bit. Okay, so that's essentially one example. If that's not the case, then you end up with something that's distorted. So if I go back to the Q9 element, where is the Q9 now? Or Q8 element, sorry, not Q9, Q8. If I look at this Q8 element here, I can see here essentially this is a distorted element. So the one thing is it's not a nice rectangle or square or not a nice parallelogram, so I know this is distorted. The other thing, the way we can distort it is what we saw with the 1D elements, is when this mid side is not in the middle between those two edges. If it's not in the middle, it's another way to distort it. So there's two mechanisms of distortion of an element. That is essentially when we start deviating. Well, let's maybe call it three ways. So the one is when we start deviating from a nice square, rectangular, or parallelogram kind of shapes. The second way is when we have curved edges. third way is when these mid-side nodes are not in the model. Those are all factors that contribute towards a non-constant Jacobian, and if the Jacobian is not constant, we have a polynomial divided by polynomial. Why is that the case? Why is the polynomial divided by polynomial? I'm just going to point this out to you, and then I'm going to conclude this for now, because we're at 10 minutes. There's a determinant of the Jacobian, okay, for this transformation. When I go and look at this B matrix, where's this B? B was, where would you write down B? You just can see it with your own eyes. I just want to point this out to you. You can see the beauty of this. When I look at the show, this is essentially, where's this nice description for the B? Okay, that doesn't matter. Yeah, remember B is just A, G, okay? Here's A. So each A has a 1 over determinant of Jacobian. So one of the determinants of Jacobians here will multiply with the determinant of Jacobian of the integration, dx dy transformation. There's another one, because remember we have two B's here, B transpose B in this integral. So there's always going to be a 1 over the determinant of Jacobian that's left, because one will cancel out with this one, and the other one will be remain. So I sit here with a divide by 1 over the determinant of Jacobian. If that 1 over the determinant of Jacobian is not a constant, but a polynomial, I don't have a polynomial anymore, but I have a rational function. A rational function, Gauss quadrature, is inexact for that. Okay, we make a mistake. So that is important to understand. So that's really how things are related. I just want to make sure that we understand sort of what to expect, what to see, and how to reason about things. Now I've equipped you with reasoning skills when it comes to these elements. So now you can go and open up any kind of element and start reasoning with it. So there might be some funky elements that, like the assumed stress element, where we don't only have an assumed displacement field, but also sort of another field that we assume independently for the stress, and we relate that back to the displacement in a weak sense, weak form. Very simple to understand, but not something we can do in this course. But what I'm saying is you'll be equipped, if you stay away from the assumed but just the displacement based elements, I've equipped you 100% to understand all of them now. You can now go and open up an element that you've never seen before and really make sense of it, without having to stress too much. Okay, there's another aspect that is just maybe important to talk about, and that is, so let's see, where it's somewhere here they talk about degenerate elements. Where was it? There's a, oh yeah, so I think let me just see if I can find that. So I'm going to point out this concept of degenerate elements. Oh yeah, here it is, degenerate quadrilaterals. I just want to talk about this. There should be a picture here somewhere actually. But essentially, if I have a quadrilateral and I collapse this mid-side node onto this line, this element becomes degenerate. The Jacobian, the determinant of the Jacobian becomes not unique. Okay, so we start ending in situations where the determinant of the Jacobian is not properly defined anymore. Okay, but our saving grace is usually, when things become a little bit degenerate, is that we only evaluated all those Jacobians and all those things at the Gauss quadrature points. So as long as things are well we evaluated there, because we only evaluate that whole expression for the stiffness matrix at these points. As long as these points are evaluatable, we're fine. But technically, the Jacobian might become already sort of singular, so it might not exist. It might become 0. So 1 over the term of the Jacobian would be infinity. So sometimes we can handle a bit of problems and degeneracy in the elements, because it only first has to reach, the impact of that has to reach these quadrature points when we evaluate them. They have to be influenced sufficiently that they go bonkers and off the rocker. Okay, so hopefully this is giving you a good idea of what the 2D elements have to offer, and it's really just based on proper reasoning from the 1D side.